at Misuses of Statistics. You may want to pause the video and read the problem. It's pretty lengthy. And then we can talk about what your comment on the overall validity of the graph is. So to summarize, this is a double bar graph, and it shows the results for boys and girls on a mathematics test taken in 2018 in 6 selected countries and Hong Kong. And what you need to do is base on the overall graph, comment on the validity of the argument that boys are inherently better than girls at math. So one of the things that should stand out to you when you look at the graph is that in the United States, boys do outperform girls. But that's not the case for all of the countries. So if you look at Finland and Hong Kong, the girls actually outperform the boys. And what's interesting too is the girls in all of these countries outperform the boys in the United States, right? So, if the differences were inherent, we would expect each of these, the percentage of girls to be greater than the percentage of boys each time, and it's not. So, the statement that boys are better than girls at math is not necessarily true because of that reason. Something else to kind of think about is that the overall differences in the scores make it seem much more likely that any gaps or characteristics could be attributable to cultural factors or even educational practices, right? Because those things vary from country to country. So if you look at the graph, this kind of justifies the fact that boys necessarily aren't better at math than girls. There's a lot of cautions we need to be aware of when we're looking at graphs or even pictures. So here's some that you may see, and you could see these in magazines, newspapers, social media, all over. One of the things we need to watch out for are what are called perceptual distortions. So what's going on here is it's showing you the declining value of $1 over time. And the problem is that the values are represented by the lengths of the dollar, but our eyes focus on the areas. So it kind of gives us a distorted view of how the value of the dollar has declined over the years. And this distortion is named after a German researcher. And basically it translates to the old goosing up the effect by squaring the eyeball trick. So, the length represents the decline, but certainly the area of each of those dollar bills is not proportional. Another caution we need to look at is when axes exaggerate. So here we have women as a percentage of all college students. Okay, both graphs show the same data, except one of the things that you may notice is that here the vertical axis doesn't begin at 0, it begins at 30. And it should begin at 0, right? It also doesn't end at 100%. So it's kind of like it's just giving us a little, snippet of the actual graph. And if you look at the graph, right, same graph over here, the axis, the vertical axis was changed so that now it goes from 0 to 100. And you can see just as many years, right? But this time you have the full picture. And one of the things that you may notice here, it shows that there is an increase in the number of women that go to college, but it's not as dramatic as this actually shows. So that looks way more dramatic. This piece here is the same as that piece there. And as you can see, it's not as dramatic. And then it starts to kind of increase very, very slowly and then maybe level out at one point. So those are things we want to be aware of when we are looking at graphs. So let's kind of wrap up that little piece there. I want you to look back at the graphical display in example 1. So that was the double bar graph, which we talked about in the last lesson. The actual mean scores on that mathematics test for US boys and girls were 482 and 474, respectively. Okay, so boys had a mean score of 482, and then girls had a mean score of 474. How does this actual difference compare to the difference in the heights of the bars shown? So in other words, this little difference that I see here, is it really proportional to how different the scores are overall, right? It looks like it should be a dramatic difference, but it might not be. So the way we can check that is by looking at what's called a relative difference. And the way we find relative difference is we take the compared value minus the reference value, and then we're going to divide that by the reference value. It's a generic formula, very similar to when we were finding percent change. So here our compared value is going to be the 482, and our reference value is 474. And now I'm just going to subtract 482 minus 474, which gives me 8. And then 8 divided by 474 gives me like 0.017. So if I want to make that into a percentage, I would just times that by 100, and it comes out to 1.7%. So what that means is that the boys' score is only 2% higher than the girls' score. But if you look at it, right, so there's only a 2% difference right in here. But if you look at it, it looks much more dramatic than that. And you can do the same for the other ones too. So the graph is distorted. We would want to see, that there's a smaller gap there, smaller space between the two bars, the heights of the bars. Something else we want to be aware of are what are called non-linear scales. So linear has a constant rate of change, right? So non-linear doesn't. It's scales in which each increment does not represent the same change in value. So for instance, here we can see that it's increasing by 10 each time, and that's all the way up the whole graph. And then horizontally, we can see that there's a difference of 20 years here, and that's consistent. Now, if we look at this graph, everything looks okay on the horizontal axis. Everything is increasing by 10. But if you look at the vertical axis, it's not increasing at the same rate. So it appears linear, which means, we would expect it to increase at the same amount. But each of these vertical, we call them tick marks, represents a 10-fold increase. So what that means is you would multiply by 10 each time to get each of these numbers. So 10 times 10 is 100, 100 times 10 is 1,000, 1,000 times 10 is 10,000, and so on. You can also think of it as powers of 10, right? 10 to the first, 10 to the second, 10 to the third, and so on. So what we call this is an exponential scale or logarithmic. And it grows by powers. Okay, so we can see here that it doesn't look very linear when you compare it to here. Here you can see that there's a much more exponential pattern to it when it's changed to linear. Okay. Let's look at percentage change graphs. So here we have changes in college tuition and then actual college tuition. So on the left, we see the annual percentage change. And on the right, we see the actual tuition. So what do you think about this one? Like, what is this graph trying to show you? The graph might make you think the public college tuition decreased like in the early 2000s, right? But the vertical axis is showing percent change. So it tells us the tuition was increasing here, for instance, in smaller amounts, but it's not decreasing. Okay, so like here, it's not actually decreasing, it's just not increasing in large amounts like it was over here, since it's showing us percent change. Okay, so it's the actual enrollment is not going down, it's just not increasing at a higher rate as it would be over here because it's percent change. So that can make it very tricky when you're reading it. So let's use those pictures to answer the question. For the time period shown in the figure above, in what year did private college tuition increase by the highest percentage compared to the prior year? And in what year was the actual tuition the highest? So if we're looking at question number 1, in what year did private college tuition increase by the highest percentage compared to the prior year? Okay, we're looking for private, so we're looking at the blue. And we can kind of see that in 2000, 2001, 2002, right? The tuition increased by the highest percentage compared to the prior year. Okay, so that's for private. So that's academic year 2001, 2002. Okay, and you can also see over here, using this graph B, right? This is showing us the actual college tuition. So you can see private is in blue, and in 2001, 2002, the tuition for that private college increased by the highest percentage compared to other years, right? Like this was the highest bar. If you look here now, there's just a little bit of a difference. So that's showing a small increase, and then another smaller increase, and so on. So that was the largest increase. And then for question 2, in what year was the actual tuition the highest? So here, if we look at figure B, the tuition was the highest in 2020 to 2021. And that's easy to see because that's where the bars are the highest. And that's for both private and public colleges. And it appears that the tuition was approximately maybe around 38,000, so around $38,000 a year. Let's take a look at some pictographs. So I'm sure you can imagine these are just graphs with pictures, right? There are graphs that are embellished with additional artwork. And that additional artwork, that can make the graph more appealing. But it can also make it misleading. Here's an example. So the figure is a pictograph, and it shows the years in which the world has reached or is expected to reach billion-person milestones. So in 1804, the world population was 1 billion. In 1927, it was 2 billion, and so on. So they're predicting by 2037, there will be about 9 billion people in the world. Discuss which aspects of the pictograph represent real data and which are statistically meaningless. Also, discuss any ways in which the data are potentially misleading. So we know that this is called a bar graph, right? And the bar graph is showing real data, okay? And we can even see that it's increasing. And it looks like the differences between the heights is approximately the same going throughout if we just eyeball it real quick. So there's no distortion there. So the bar graph shows real data. But the artwork here, like all the people, the globe, it's kind of meaningless. Actually, it is meaningless. So, the population looks like it has risen linearly, but the intervals between the bars vary greatly too. So that's something else we want to look at, right? Like, it's not the same number of years between each of these. Like, there's not the same distance between 1804 to 1927 and then 1960 to 1974. So it's not a linear increase. So that's something else that can be misleading. Okay, so artwork makes it nice, but it's statistically meaningless. As we said earlier, the bars appear to be reasonable, representing the population, but the population looks like it's risen linearly, but the intervals are not the same. From here to here, there's 123-year difference. And then from here to here, there's a 33-year difference. So, but it looks like it's linear, and it's not. So population looks like it has risen linearly, but The intervals between the bars vary greatly. Okay, we looked at some graphs. We looked at how they could be misleading. We also want to analyze statements. So anytime we have any kind of statistical statement that you read or that someone says, you want to analyze it before you accept it as a fact. So you should always ask yourself two questions. The first one is, was the sample used to gather the data unbiased and of sufficient size? So what we mean by unbiased is like favoritism. Was the wording of the question in the survey, leaning more towards one group than the other? So you have to be really careful how you survey and ask questions. You know, because if you have bias in your question, you're going to have bias in your results, and then it's useless. Our job in statistics is to find out information about the population based on samples. So if your sample is biased, your analysis will be biased, and then you don't know anything about the population. And when we say sufficient size, we just want to make sure our sample size is large enough. So it's not like you did a poll and only 4 people responded, right? We would need a much larger sample to be able to determine anything. It's impossible to make sure that your sample is completely unbiased, but we can do the best that we can to make it as unbiased as possible. So you always want to check for bias in your samples, make sure the sample size is large enough. And then, is the statistical statement ambiguous, right? So that means can someone interpret it more than one way? That would affect how they're going to answer it. So we'll say question or statement ambiguous, right? And we mean, can it be interpreted in more than one way? So if you're structuring a survey for someone, you need to make sure that the statement's not ambiguous. And also, when you read statements, you need to make sure that they're not written in an ambiguous way, because then you also don't know, what information is being said. So here are some statements, and what I'd like you to do is pause the video and read through them and tell what possible misuses or misinterpretations could exist from each statement. In a recent study of patients with cold symptoms, each patient was found to have improved symptoms after taking honey. Therefore, honey cures the common cold. So the problem with this statement is, first of all, when they say in a recent study, was the sample unbiased? Was it large enough, right? But not only that, you can't say that honey cures the common cold. You would need to perform an experiment to do that. And that's difficult to do. So the patients, they might have improved on their own without taking the honey. We don't know. So that's a misleading statement to make. Most accidents occur on Saturday night. That means people do not drive carefully on Saturday night. So the problem I have with that is, if you think about Saturday night, the weekend in general, I would expect more people to be driving, right? Because people are out and about. So you might expect more accidents there. At Orange County High School, half the students are below average in mathematics. Therefore, the school should receive more federal aid to raise student scores. Well, if you think about this statistically, right, if you were to graph the scores on a large test, like a standardized test is probably what they're talking about here, you're going to have students who score average. You're going to have some students who score a little higher and some students who score a little lower. But you would expect 50% of students to score higher and 50% to score lower. So half the students in a population are expected to be below average. That's not uncommon. You know, that could be like the same thing with the average height of, let's say, males. There's an average height in the world. Probably 50% of men are taller and 50% are shorter. And we know this because we've done research and graphed it, and it comes out looking like a bell curve, as do many different samples of large populations. They will come out as a bell curve, and then one of the properties of a bell curve is it's symmetric. So that means it's the same on both sides. So 50% would be on the right, 50% would be on the left. So that, to make a statement that half the students are below average in math, well, that might be true. That also means half or above, right? And then the last statement, healthy snack cookies are fat-free, so eat as many as you like and you will not gain weight. So that might lure people in to buy the product. However, you're dealing with cookies, right? They might be fat-free, but they still contain calories. So, you know, the more calories you consume, the more weight you're going to gain. So when you increase your calories, you gain weight. And that's pretty much it for this lesson. So beware of, you know, graphs that you see and statements that are made, because they can be misleading. And now you have some statistical knowledge that you can apply to those things, you know, not to take things, you know, right away without looking into where did this sample come from? Is it unbiased? Was it large enough? And then, you know, was the statement or the question asked, was it ambiguous? Because if it is, then it's not a good question. Have a great rest of your day. And if you have any questions, please reach out.